Hi, in this lesson we're going to take a look at how to work out the total resistance of circuits containing several resistors in a mixture of series and parallel combinations. For example, the one on the screen at the moment. In order to understand the lesson, you have to be familiar with how to combine resistances in series, and I hope you know that the total resistance is equal to the sum of the individual ones. You also need to be able to cope with resistors in parallel, so I hope you know that the total resistance is given by 1 over the total is 1 over the first plus 1 over the second, and so on. We can take that formula for two resistors and simplify it to get the total resistance. We get this very handy formula in the middle. If we have two resistors in parallel, the total resistance is simply the product of the resistances divided by the sum of the resistances. And that's very useful when you have two resistors in parallel, but it doesn't work for more than two. You can't extend that to 3. You can't use R1 times R2 times R3 over the sum R1 plus R2 R3. It doesn't work. It only works for two resistors in parallel. The other thing you might want to note, it often saves some work, is that if you have a number n of equal resistors, suppose that each have a resistance R. If they're in parallel, the total is simply R over n. For example, if I have two resistors of 15 ohms each in parallel, the total resistance is 15 over 2, 7.5 ohms. And that can save some work sometimes. Okay, now if you want to get a pen, paper and calculator, you might like to try this for yourself before I even show you the solution. This is a pretty straightforward one. You might be able to guess how to do it, and if you want to pause the video to try this for yourself, you can do that now. Well, let's go through it. We've got a cell with an EMF of 2 volts. Basically, think of that as voltage of 2 volts. 3 resistors, and we need to find out what the total resistance is and what the current through the cell is. The first thing to do is to spot that the 4 and the 3 are in series, so we could replace that 4 and 3 by a single 7 ohm resistor. Let's redraw the circuit showing that. 1 ohm and now a single 7 ohm resistor. And I hope you can recognize that the two resistors are now in parallel. And I've drawn it this way to point this out, because I know some students struggle identifying resistors in parallel. If we simply take the top resistor and reposition it, move it down the side, it's easier to see they are in parallel. So how do I work out the total resistance of a 1 and 7 in parallel? Well, the easy way is to use the handy formula product over sum. 1 times 7 over 1 plus 7 is 7 over 8, and that's 0.875 ohms. In an exam, it would make sense to say, well, these values are given to two significant figures, so I will give my final answer to two significant figures, 0.88 ohms. We also want to know the current. Well, the EMF, the voltage, is 2 volts. The resistance is, I won't use the rounded value, I'll use the accurate value to avoid rounding errors. The resistance is 0.875 ohms. So current is 2 over 0.875. It's 2.3 amps to two significant figures. Here's another circuit to try. Again, if you want to pause the video, you can try this for yourself before I go through the solution. You can do that now. Okay, we've got a network of resistors, and we want the total resistance between A and B. Let's look at the network. Can we identify any series resistors? Yes, we can. The 3 on the right are in series. Also note they're in kiloohms. 3, 7, 20 in series. Well, that adds up to 30. So we're going to start by replacing the 3 in series by a single 30 kilo ohm resistor. And now you'll see that the three resistors on the right are in parallel, so we can combine those to find what the total resistance is and replace them by a single resistor. Let's do that. 1 over the total is 1 over the first plus 1 over the second plus 1 over the third. It's 1 over 10 plus 1 over 20 plus 1 over 30. And you can do that as a fraction if you're good at fractions. You can enter it directly into a calculator. The answer comes to 0.183 recurring. I've just given an extra decimal place here to reduce rounding error, but the answer is 0.1833. And that's the answer. That's the value of 1 over RT. To get RT, I've got to remember to invert that value. So RT, the total resistance of those three resistors, is 1 divided by 0.1833. It's 5.45, and the unit is kiloohms. So I can replace these three resistors by a single one, 5.45 kiloohms. And that leaves a very simple circuit. Two resistors in series. So the overall total resistance is 10 plus 5.45, 15.45 kiloohms. Again, probably want to give the answer to two significant figures, the same as the data originally provided. And the best answer, I think, is 15 kiloohms. Okay, a final problem. This is a harder one. You'll need a little bit of algebra to do this, but if you want to try it, pause the video in a moment and see if you can do it for yourself. I'll just read through the problem. We've got 10 resistors, and each one has a resistance R, and what you've got to do is prove that the total resistance, that's the resistance between the wires on the left side, the top and bottom, prove the total resistance is 5R over 4. Looks a bit daunting. It's not that difficult. It's a bit fiddly. If you want to have a go, pause now. Well, let me give you my solution. First of all, look for series resistors. These two on the left can be replaced by a single 2R resistor. These two in the middle can be replaced by a single 2R resistor. And the 4 on the right hand side are in series. They can be replaced by a single 4R resistor. R plus R plus R plus R is 4R. Let's do that. Now, hope you can see we've simplified the circuit quite a lot. Next stage, what can we get rid of? Well, the two resistors on the right are in parallel. So let's combine 2R with 4R in parallel. Use our handy formula, product over sum. We're going to multiply 2R by 4R and divide that by 2R plus 4R, which gives us 8R squared over 6R. That cancels out to 4R over 3. And that's the value of the two resistors on the right. Redraw the circuit. And now we've got three resistors in series, R, 4R over 3, and R. We can get rid of those by adding the resistances together. R plus 4R over 3. If your basic algebra is okay, you'll know that's 10R over 3. And now we're down to simply two resistors, 2R and 10R over 3 in parallel. Let's combine those. 1 over the total is 1 over the first plus 1 over the second. I've decided to use this formula because it's a little bit simpler to manipulate than the product over sum. So I'm using this formula. Put the numbers in. The first resistance is 2R, so it's 1 over 2R. The second resistance is 10R over 3, so 1 over that is 3 over 10R. So the second term is 3 over 10R. And I've got to add those two fractions, 1 over 2R plus 3 over 10R. Let's choose a common denominator of 10R, and if we do that, that becomes 5 plus 3 all over 10R, and that's 8 over 10R. And that's the value of 1 over RT. To get RT, I've got to invert that. RT is 10R over 8. Cancel 2's top and bottom, and we get RT is 5R over 4. which is what we set out to prove. Finally, let me just point out that not all circuits can be solved this way. Not all combinations of resistors can be added. If I had a circuit like this, which is a way of showing what's called a bridge circuit, you can't use the series and parallel formula to work out the total resistance. And if you look at that and try it, you'll probably see why. You can in one special case where the values are such that there's no current going through that middle resistor, but in general there is no way to work out the total combination of this using the series and parallel formula. It can be done, but we have to use what are called network analysis techniques, and that's not within the scope of what we're doing at the moment. So simply be aware that not all circuits can be worked out. Total resistance can't always be found using the simple formula we've been using. Well, that's it. I hope that was useful. Thanks for watching.